Now we'll talk about Turing machines. A Turing machine is just like a finite state machine in that it is an abstract model, not a physical device. So it's an abstract model that can be used to represent processes present in a physical device. To understand a Turing machine, you need to imagine a tape made up of individual cells, like you see here. There's a leftmost cell, but to the right, the tape theoretically goes on and on forever. Each cell in the tape can have a symbol in it, or it can be left blank. If it's left blank, we put in an asterisk, which basically represents that we're keeping that blank. At some point, after a finite number of cells with symbols, the rest of the cells to the right are filled with blanks. So you see in this example, we've got all of these blanks here at the end, and we're assuming they go on and on forever being blank. Now there's a head that moves back and forth along this tape, looking at the string of symbols. The cell that it's pointing to at any given time is called a current cell. Now, in the current cell, when the head is pointing to it, the head can read the symbol, can tell what's in that cell, and it can write in a new symbol if it's set up to do that. So it can read, and it can even replace with a new symbol. And then after it does those two things, then it will move either right or left to the next cell over. So it'll either move one cell to the right or one cell to the left. This is a very interesting website that I found that has some really great examples of Turing machines. I'm going to go ahead and play this video so that you can kind of see what is going on when you go to these Turing machines on this website. So here you see there's this long tape, and there's symbols in there. And what this particular Turing machine is doing, you can see it says up here, even amount of zeros. It's determining whether this input string has a even amount of zeros. Here's another one where it's going to use a Turing machine to convert a decimal number into a binary number. So I put in a 3, and some things are going to be done. We don't know what it's doing. You can look later, go back to that website and try to figure it out. But that's really not the point here. The point is to know that a Turing machine can do something like this. It can take a decimal number, turn it into a binary number by only doing what we've just said, looking at this tape and moving back and forth along this tape and either writing new symbols or reading each symbol and then possibly rewriting a new symbol in there. And I started out with a 3, and it ended up had to go back and forth several times, ended up coming up with 1 1, which is the binary representation for that number 3. Now, this theoretical machine we would consider to not have any other place where something could be saved in memory. So all of the memory that would be that that a Turing machine would have at its disposal is just what's written there on the tape. So we can consider the one-dimensional tape and its contents to represent what's in the memory. There's a couple of different alphabets that we'll talk about here next. There's something called a tape alphabet. Basically, a tape alphabet for a given Turing machine is just the set of symbols that can possibly be written to a cell. Okay, and we'll call that gamma for the tape alphabet. So it doesn't mean what's there now, it's just what possibilities there are to write for that particular Turing machine. Now the tape alphabet has to at least have a blank symbol. We know that blanks are put into Turing machines, so it has to have a blank symbol in there and at least one other symbol. Otherwise, that would not be very interesting. Everything would just always be blank. But we've got a blank and then at least one other symbol that would represent the set of symbols that can be written to any given cell within on that tape. There's also the alphabet called the input alphabet, and that just is it's represented by sigma, and it's just made up of the symbols that show up in the initial input string. So maybe at first all you see are A's and B's, but maybe there are capabilities for that Turing machine to also add in C's and D's, right? So the C's and D's would be considered part of the tape alphabet, but the input alphabet is just those symbols that are there at the beginning. So if it only started with A's and B's, that would be what what would be considered part of the input alphabet. Okay, so this says here, note that the initial input does not necessarily contain all of the symbols that are in the tape alphabet. So symbols that are not originally there but exist in the tape alphabet can be written onto the tape. A Turing machine has different states, just like a finite state machine has. So, and it's going to be a finite set of states. And again, just like with finite state machines, we're going to denote that set of states with a capital Q. And now the set Q for a Turing machine is going to include several different states, but at least these three special ones. Q naught, which is the start state, and then QACC, which is called the accept state, and QREJ, which is called the reject state. So sometimes with the Turing machine, we're seeing if some input string would be accepted or not. And so in that case, we would use either that QACC to say yes, the input was accepted, or QREJ, which is saying that no, the input was rejected. So here's some examples of what might be considered a state at any given point. And it would be different depending upon what situation we're in and what exact Turing machine we're using. But these are just some examples that might be considered a state in a certain Turing machine. Maybe a certain character has been observed on the tape at least once, and maybe we care about that. So if we care about that, then that would be something that we might want to keep track of. Or a certain character has been observed on the tape a certain number of times. So maybe it's been observed 3 times or 5 times, something like that. A certain character has not been seen yet, or the input string represents a valid password. So these are just different examples of different states that we might see in a Turing machine. And it's possible, we've listed those with sentences above, but it's possible we could have a Turing machine where the states really aren't anything that we can put into words. Okay, so it's possible that the states are just named, like, okay, we're going to say that it turns into Q2 if a certain letter is encountered or something like that. So sometimes those states are just named and we really don't have a way to describe them in words. Now the configuration of a Turing machine consists of the contents of the tape, the current state, and the tape cell to which the head is currently pointing, which we would call the current cell, right? So we've got a current state, a current cell, and the contents of the tape at any given time. Now, one thing we haven't talked about yet, but what we would need, just like with the finite state machine, we need some kind of rules in the background so that we would know what happens when this head encounters certain symbols. And how do we know, does it move right or left? And how do we know, does it put a new symbol in there or not? That's the kind of thing that the transition function is going to tell us. And again, it's called delta. For this case here, for a Turing machine, we're going to have two types of input that go into the transition function. We have what's the current state and what's the current symbol. Again, current symbol means what symbol is being pointed at by the head. What comes out of that transition function? Several things. A new state. Maybe the state has changed. Sometimes the state stays the same, but it'll say what state it should be, given that input that has just happened. So some kind of new state, a new symbol that should go into that cell. And again, sometimes that new symbol happens to be the same symbol that was already there, but we could just consider it a new one, but it might just be the same. And then we need to know, because we need to know what's the new state, what's the new symbol, and then we need to know whether that head should move to the right or to the left. So that all of those instructions need to be part of our transition function. Given a certain input, what should happen? Now, in the book says, and we said here at the very beginning, that the tape is going to have a leftmost cell. Now, if you remember back in that video that you just saw, where we looked at that website, it actually showed blanks to the left and made it kind of look like it goes forever to the left with blanks. And that's another way you could see it. But in the way the book describes it, no, we're going to pretend that this tape that we're imagining has a leftmost character. So the question that you might have would be, what if the head is at that first character and somehow it gets instructions that it should move to the left, but there's no other symbol to the left? So here's what this is saying. If the head is supposed to move left and is already in the leftmost tape cell, then the head stays in the same location after the step. So it won't move, it will just stay there. So that's the rule in case we get to that point. Here's an example of what a transition function might look like. I don't want you to worry yet. You might read the top here and see that it says transition function for Turing machine that recognizes strings with 2 B's. That is what this transition function is, and we're going to actually be looking at that very situation later. But don't worry about it right now, and don't try to think, well, how do you come up with all of this? We're actually going to come up with all of this. But for now, just realize that this is an example of a transition function where we've got some input, and then we would find what the output would be too. Remember that in this case here, with a Turing machine, we've got two types of input. We've got the state and the current symbol. So what these tables need to do is allow us to specify what's the current state, what's the current symbol, and then what does it need to spit out? It needs to spit out a new state, a new symbol, and then instructions to move either right or left. So if you look here at this table here, we're just going to look at one of the cells. And again, don't worry about how we come up with this because we'll come up with it later. But what that means is it's there at the intersection of the state Q0 and the symbol B, right? We would get to that place by starting with the state of Q0 and the symbol B. What does it say in there? It says Q1BR. That means this is what's coming out of the transition function. That means that the new state is Q1, the new symbol is B, and that we should move to the right. Okay, so that's what, if you see all these things in these cells, that's what those three things mean. The new state, the new symbol, and whether to move right or left. Now, if we do have a situation where we're trying to see if there's some property is there, and we would either find that the input was accepted or rejected, then we would have the QACC and QREJ, and once that either of these would be encountered, at any point if one of these would be encountered, then the Turing machine is going to stop completely. So you see over here you see ACC and REJ. So once you would get to those, you would be done. If the Turing machine does eventually reach that accept state of QACC, after starting with a particular input string, then we would say that the Turing machine accepts that particular input. Yeah, if we're calling the input string X, then we'd say that the Turing machine accepts X. If we have an input of a string that we're going to call X, and it reaches the reject state instead, then we would say that the Turing machine rejects X. And if the Turing machine reaches either the accept or reject state, we would say that the Turing machine halts on input X. So it would be halting, and that means that it's either going to be accepted or rejected. We're going to look at a simple example where we're going to consider a Turing machine that will take an input of a string of characters that only consist of A's and B's, and will accept the string if and only if the string has at least two B's anywhere in the string. So I'll input some string of A's and B's, and it's going to be accepted or rejected. It'll be accepted if there's two B's, at least two B's in there. If not, it'll be rejected. So we would say that the input alphabet is this set AB, and the tape alphabet would be AB blank, because we can be putting blanks in there if we would need to. I don't think we aren't going to need to in this example, but officially the tape alphabet always includes that blank symbol. Now we're going to have some different states. Here's how we'll set this up. Q0, for one thing, that's the start state, which we always know, but also Q0 is going to going to mean that no B's have been seen yet. And that makes sense. If we're in the start state, we're going to start over on the left-hand symbol, and before we've looked yet to see what's there, we will have found no B's, right? So it makes sense that Q0 would be the start state. If we've encountered one B so far, we're going to say that the state will then be Q sub 1. That means one B has been seen. Now, what if we've seen not 0 B's and not 1 B, but what if we encountered 2 B's? Well, that's important because that's all we're caring about here. All we want to know is, does a string have at least 2 B's? So once it has encountered 2 B's, we wouldn't bother calling that Q2 and then keep counting or anything because we've hit we've hit what we're looking for. We've found two B's. So we're going to call that the accept state. That's the QACC. So QACC means that two B's have been seen, and so we would say then that the Turing machine accepts that particular input string. But if we go through this, and we'll see how it's done here in a minute, if it gets through this whole tape looking at all of the symbols and goes all the way until it starts encountering those blanks and has not encountered two B's, then we would say that we know that there are not at least two B's in this input string, and so we would say that we should have a rejected state, and so we would have the QREJ for reject state. Okay, so the head is going to start over there on the left, and right now it's going to start at the start state of Q naught. And notice this, as it moves along, we don't need it to ever change any symbols. In this case, all it's doing is counting B's. So there's no reason we would need to change a symbol and erase a B and put an A in there, right? So in this case here, the tape contents are never going to change. That's not always the case with the Turing machine. Sometimes those symbols change, but in this case not. So if the Turing machine is in this state of Q naught, like it is right here in this picture, and then the head takes a look to see what's in that current symbol, as it will right now, and it encounters a B, like it does, because in that first cell there is a B, then what would you think might happen? That Q naught is going to turn into Q1. It's going to have a new state because it has seen 1B. So it would turn into, the state would turn to Q1, and what would make sense? It would make sense to move 1 to the right because there's no reason to move to the left. So we would move to the right. So now that's what we've done. You see how the state has changed to Q1 and we've moved to the right. And we'll just continue moving to the right. So now we've gone on to the third symbol, and when we first get there, the current state is Q1 because it has already seen a B, but now it's at this third symbol and it sees another B. So that state's going to change to a Q2 and then move to the right. Okay, but the fact that it's just found its second B means that we don't have to keep going, and we would say that we've reached QACC, the accept state. And we can stop. We don't even have to keep going no matter what's to the right because we have found at least two B's. Now, what if this continues to happen, but there aren't two B's in the input string? Then we would keep moving over further and further, and once we reach one of those symbols of an asterisk, that means it's encountered the end of the input string. If it gets to a asterisk and it's still in Q0 or Q1, then that's when we know that means that there are not at least two B's. There's either no B's in there or there's one B, but it never got to two B's because it never reached the QACC. So here's what this last sentence says. If it encounters a blank or an asterisk symbol while it's in the state Q0 or Q1, then the Turing machine has reached the end of the input string without having seen two B's and therefore transitions to the reject state. So this particular one that we just looked at had an input string of BABAA, and we would say that this Turing machine accepts BABAA because it did get to the accept state as it went through that process. But let's go through it again with a different input string. So it's just an A, B, and an A. So we start in the initial state, Q naught. It hasn't seen no B's. Here it looks first and it sees an A. So it knows that no, it has not seen a B, so the state is going to stay the same and it's going to move one cell to the right. So it moves to the right. See, it does see a B now, so it's going to change, the state's going to change to Q1 and move to the right. And now it sees an A, so now the state doesn't change because it's still just seen one B, but it's going to move to the right again, and it's going to encounter a blank symbol. And so the blank symbol tells us that it's reached the end, and it never did get up to Q accept, so we would have to say it's rejected. So we would say the Turing machine rejects ABA. Now we've kind of talked through this example, but we're going to go a little step further because we kind of talked through it, but we don't have an official transition function written down anywhere. We just said, you know, if it hasn't seen a B yet, then change it, and it does encounter one, change it to Q1 and so on. But let's come up with this little chart that will actually show everything, all the possibilities. And this is actually that chart we saw a few slides ago where I said don't worry about how to come up with those. We're going to come up with them right now, okay? So remember, this transition function in this case here for this Turing machine is going to accept some input of the current state and the current symbol, and then the output's going to be a new state, a new symbol. Again, those states maybe end up not changing. Maybe it was a certain state and then the new state is the same one. So when I say new state, it doesn't mean that it's always changing, but we're going to call it the new state. So new state, new symbol, and then instructions whether to move either right or left. Okay, so let's look right here at this first cell when it's right at the beginning. The state is Q naught, and it's seeing an A. So we're going to then have this chart here where we have the states over on the left, the symbols on the right, the symbols at the top, and we would want to look for Q naught and A, right? Because that's where we're at now. We have a Q naught as the state and the symbol is A. So that's going to be right down here, this top left blank area here. So let's think about what should happen if we encounter an A when we have Q naught as the statement. Well, what should the new state be? Think about it. What should the new state be? We don't want the state to change, right? Because it's just seen an A and it's counting B's, so it should stay the same. So the state should be Q naught because it just saw an A. Now what about the symbol? Well, this is that same example we just talked about where it's just counting B, so it's not going to be changing any symbol at any time. So whatever the symbol was that it encountered, it's going to keep it that way. So the new symbol is going to be whatever was there to begin with. So we just saw an A, so it's going to stay an A. Now, do we move right or left? Well, what we're going to do in order for it to get through this entire input string is have it move to the right each time. So we'll say R for right. So if it encounters an A when it has a state of Q naught, then it's going to stay at Q naught, going to stay at A, and it's going to move to the right. Okay, so let's move it to the right here. If it moves, I guess I didn't show this head moving up here on my animation, but imagine that head moving over to the right there. So then Q naught would be the state, but now we would be encountering a B. So then what? Well, that's when this Q1 is going to come up now. The original, it was a Q naught, and we just encountered a B. So now that's a Q1. Again, we don't change the symbol, but we move to the right again. Let's see which one I went to next. Okay, I went to the situation where we have, let's say that we have a state of Q naught, and I've just encountered a asterisk. That means I've got to the end of the input string. Well, here's where we would change now. What would be the new state? If we get to the end and have not found two B's, then we're going to reject this input string. So we would want to put QREJ there for the reject state. What's going to be the new symbol? Again, in this example, we don't ever change the symbol, so it would stay at the blank. Now what are we going to do? Because we're done, right? We're done. But we got to say we're going to move right or left. And this is very arbitrary because we're done. But we're still going to move either right or left. Now I could just as easily say, well, let's just continue to move right, and then we're just going to stop after we move right one more. But the book's example, and this is an example here that I got straight out of the book, they have an L there. So what does that mean? That just means they arbitrarily decided, well, when you get to the end and you find that it's been rejected, let's just move to the left so that we're at the end of the input string. This is so arbitrary, right? I mean, it doesn't matter because we're done. But that's what they decided to do. Okay, so we're going to say once it's rejected, we move to the left so that we're pointing still at the end of the string. Okay, let's go now to the next line. What if we've encountered, what if we have a state of Q1? So I don't have a picture what's going on up here at the top, so you don't need to look at that and try to make that look like where we're at. We would already be somewhere else, and we would have already encountered a B. But what if we got a Q1 and we encounter an A? Is that going to change the state? No, that doesn't change the state. The state would stay at Q1, right? Because we've already seen one B, but we haven't seen another. We just saw an A. So it would stay at Q1. What's going to be the new symbol? Well, again, we're not changing symbols here, so it would stay an A. And again, we're just keep moving to the right, so it would be an R, except for those cases where we get to the very end, right? Okay. Now, what if we have Q1 state and we encounter a B? That's when the state changes to QACC because it's just found the second B, and that means it's been accepted. And then again, it doesn't change the symbol. And here again, just arbitrarily, they decided to move left there. What if we have Q1 and we encounter the end? It's just really the same thing as if we had Q naught and encountered the end, right? We'd say, well, we didn't get to a second B, so it's going to be rejected. So we have QREJ, and then we don't change the symbol, and again, we'll decide arbitrarily to move left. So hopefully you can see how we came up with all of those based on, now that you know what we're doing within this process. Hopefully you can see how we would get all of those things. Remember, what's inside these cells are the output of the transition function. What's the new state, what's the new symbol, and which way do we move? Here at the end, we're going to look at one more example of a Turing machine. This Turing machine recognizes if a symbol has been repeated a number of times that's a power of 2. So if you see here in this tape here, we've got a bunch of A's. We're going to assume that that's all that's going to be in this example. It's just some just the symbol A's. And we want to find out, has it been repeated a number of times that's a power of 2? Let's count this. 1, 2, 3, 4, 5, 6, 7, 8. It's been repeated 8 times, and that is a power of 2 because 8 is 2 times 2 times 2. So, but what we're going to need to do, this is a very much more involved, and I want you to know you're not going to have to come up with anything like this, okay? Here you just want to see me go through it. And I think this is an example possibly that there's some questions about in the participation activities or something. So I want you to be able to follow it, but don't think, oh my goodness, I would never be able to come up with this. You don't have to come up with it. Okay, so first of all, before we even get into this, we're going to use this little fact that helps us in this case. And this is a fact that if a number is a power of 2, you can keep dividing by 2 until you get a 1. If it's not a power of 2, that's not going to happen. You'll never get down to 1. Let's look at some numbers here. 8 is a power of 2. Let's see, if we keep dividing by 2, will we get down to 1? 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. We got down to 1. So yeah, 8 is a power of 2. But let's look at 6. 6 is not a power of 2. Let's try this. 6 divided by 2 is a 3. Now, 3 divided by 2, we're not ever going to get down to a 1, right? This is an odd number, and we know since it's odd that we'll never be able to divide by 2 and end up with a 1. 3 divided by 2 is a 1.5. And then we could keep dividing by 2, but never end up with a 1. Okay, so even though we might not think about it that way, that is one way we could tell, one way we could kind of maybe come up with some little algorithm that would be able to tell if some number is a power of 2. Keep dividing by 2 and see if we end up at 1. Okay, so here's how they decided to do this. Now, when you come up with a Turing machine to solve a certain problem, as I said, this example here, it's not straightforward at all. I guess if you do a bunch, you'd probably start to kind of get the hang of it and kind of be able to figure this out. But this is not something that you would know right off to do. So when you see me saying this is what we're going to do, don't worry that you would not have come up with this. So the first thing that we're going to do here is start by changing that first symbol to an asterisk. Now, usually an asterisk means a blank, but we're not going to recognize it as a blank in this. We just need to indicate the beginning of the string so that we don't keep having that head keep trying to go backwards. So we're just going to kind of put this little asterisk there in the first slot as kind of like a bumper to say don't go past here. If it's moving to the left, we don't want it to keep going, trying to go left if it's hit that beginning one. So anyway, we just put that asterisk there, but we know that it does not mean that there's really a blank there. We know that it's really an A there. Now, what are we going to do? We got to try to figure out if the number of A's is power of 2. Remember, we're going to use that fact that we can divide by 2. So what we're going to do is we're going to mark out every other A that we see. And what that's going to do is basically divide the number of A's by 2. So see how, remember that first symbol, we're going to remember it really is an A even though we put a blank there. So we're going to say there's an A, but the second A, I mark it and turn it into an X instead. Here comes another A, that's fine, but then the next one, I'm going to change it into an X. I'm getting rid of every other A. So I get rid of every other A, and then, so that is there. Now, so basically in this case here, I literally, knocked down the number of A's. I divided that number by 2. Now, here it was an even number of A's, so I ended up with an X. Okay, so let me read this here so that you can hear everything you're supposed to hear. Now we move to the right, replacing every other A with an X. As long as we can always find a second A to change to an X after seeing one A, we know there was an even number of A's and we can keep dividing by 2. If we come to an A and then find there's no more A's to replace with an X, then we know there was an odd number of A's, and so it was not repeated a power of 2 because we've come to this odd number like we did the 3 above that could never be divided by 2 and result in a 1. Okay, so basically we mark off every other A, turn it into an X, and if we come to an even number here, we get an X and then don't see any more A's after here. That's good. That means it was an even number of A's, and now we can keep dividing by 2. But if we had turned this last X that you see here, if we had turned that into an X and then came up with another A after here, but then not another one after that, then that's where we'd say, oh wait, I've got an odd number of A's, so no, it is not repeated a power of 2 times. But this one worked, right? We marked off every other A and got to an X and didn't see any A's after it. So we know that's fine. We divided the number of A's by 2, and now we have 1, 2, 3, 4 A's instead of 8. Okay, so we've done up here like what we did up here. 8 divided by 2 is 4. Okay, now what are we going to do? The head is going to start moving to the left and continue until it gets back to the beginning of the tape. How does it know it's at the beginning of the tape? Because it encounters that blank that we put there at the beginning. Once it sees that, it knows, oh, this is really not a blank, it's an A, but it's telling me that I'm at the beginning of the tape. Okay, so imagine the head going all the way back and starting again here at the left. Now again, we're going to move to the right and replace every other A with an X. So now here we only had 4 A's left. So now the first A is where that blank is, and the next A is that third cell, so we'll mark that off. And then we'll keep moving to the right until we see another A. We won't mark that off because we're only marking off every other A. But then the next A we see, we mark that off. Again, we'll keep going until we get to the end, till we start seeing a bunch of blanks over here. As long as we don't see any more A's, we're good and we're still on the right path. But remember, if we've marked out an A and then we encounter another A and can't mark the next one out, then that means there's an odd number of A's, and we're going to be able to say no for sure that it is not repeated a number of times that's a power of 2. But here again, we're okay. We marked out every other A that we had left, and we still didn't encounter a little individual A by itself afterwards, so we're still good. So now how many A's are left? 1, 2. So that represents this way up here at the top when we said, for example, 8 is a power of 2. We've gone from 8 down to 4 and now down to 2. Now we're going to do it all again. We're going to move to the left all the way to the front, and then again change every other A to an X. So we would do that one more time, and so I'm not sure that I have a picture of that, but we would then, this second A that we see in here, the tape, that would then get turned into an X as we go through it again, because we're doing every other A. And then once we do that and not see any other A's past here, then we would say, okay, how many A's are left? Just that one A that's at the beginning. And so we would say it worked. We got down, we kept marking off every other A until we ended up with just one A and never had that problem where we had an extra A at the end. So we would say that we did good. It worked. We were able to find only one A in the string, so we can say yes, that input string would be accepted. Now we're not going to go and show the transition function of all of that for this one. I just wanted you to see this process and kind of see the kinds of things that we do in a Turing machine. You can get really creative and do things. And as you looked at that website, if you want to go back to that website that I talked about earlier and look and see what it's doing, sometimes it's hard to tell what it's doing, but if you look at the book and kind of read some other different examples, you see that sometimes you have to be really creative in coming up with a Turing machine. But as I say, you don't have to come up with a Turing machine in this class. You just have to be able to understand what one is and be able to maybe read a transition function or be able to know what ends up happening if you follow a transition function. I have one more thing to say and then we're done. So there's a challenge activity for the Turing machines, and I think it's just really confusing here what they do, because they're going to have you do 4 problems. You can see by the bottom that it goes from 1 to 4, so they're going to have you do 4 problems. But they're giving you this transition function, and they also give you this input function. See up here, B, A. That's what you want to start with, and then just start through pretending like the head is pointing to this first one and try to decide which of these cells then would be the output if you start at that beginning there with this input. So what you would do, what the Turing machine would be do a bunch of steps. We start at the first one, then go to the right maybe and do another one, and you're going to do it over and over and over. For this first problem, it's only going to ask you what's the state of the Turing machine after step 1. Okay, so that's why it says step 1 here. So you're going to you're going to look at this, click on step 1, and answer in that drop down what the state would be after just the first step. Then it's not going to ask you for any other steps in that problem, for that problem. But when it goes to the second problem, when you check your answer, find out you're right, then you can go on to the second problem. It's going to give you a brand new problem here. The input value will be different, and it might very well be a completely different transition here table. So it's a completely different problem when you get to number 2. But when you get to number 2, this time it's going to ask you for the first 2 steps. So, what's the state of the Turing machine after step 1 and then after step 2? And then again, you check the answer, and then if it's right, you get to go on to the next one. So as you progress through those, for one thing, it's a brand new problem each time, and as you progress through, you have to do more and more steps. So by the time you get to the 4th one, it's going to ask you for 4 different steps. What's the state after 4, after the first step, then after the second, after the third, and after the 4th. So you have a lot more to do by the time you get to the 4th one. I would definitely suggest not trying to do this in your head at all, but writing things down. I would write, because especially, write down what the input is, and then on the next line, show maybe what the input looks like, what this tape looks like now, and what the current state is. And then, as you get to some of these later ones where you have to do more than one step, you're going to have a bunch of lines. each line representing each step. Hopefully that makes sense to you. But anyway, and you can read this slide too, but I just think it's very confusing when they only ask for one step on number 1, but then when it comes to number 2, you're going to ask for 2 steps and so on. Okay, hopefully you can do okay on this. Let me know if you have any questions.